Let's go. Chemistry Regents review. Alright, which phrase describes the charge and mass of a neutron? Okay, even if you don't know this, go to your reference guide, scroll down, and you're gonna go to table O. And table O, symbols used in nuclear chemistry. What do you have here? A neutron. This 1 on the bottom, this 0 on the bottom represents the charge of the neutron. And the charge of a neutron, in this case, you see the 0, it has no charge. It's neutral. So a neutron has no charge. So immediately, you can get rid of 1 and 2. Now this 1 right here, this represents how much the neutron kind of weighs. And the amount that the neutron weighs is about 1 AMU or 1 U. Alright, that's what the 1 stands for. It weighs approximately 1 AMU or 1 U. That's the units for it. So right here, it has no charge and approximate mass of 1 U. What's the number of electrons in a potassium atom? Well, in an atom, you know that atoms are neutral, okay? And in an atom, there are positive protons, right? Protons, they have a positive charge. And there's negative electrons. All right, so electrons have negative charge, protons have positive charge. And in a neutral atom, the amount of protons equals to the amount of electrons. So in this case, if you scroll down here, and this is what, I don't know what this table is, but you can scroll down to your periodic table and you'll see potassium. First of all, if you don't know what potassium is, here you go, element 19. So we have element 19 here, and this 19 here tells us that a potassium atom has 19 protons, okay? So the atomic number, right, all these bolded, you see these bolded numbers right here, those tell you the amount of protons in the element. So for example, element 1 has 1 proton, element 3 has 3 protons, beryllium, element 4 has 4 protons, and so on. So back to our thing, we know that in an atom, the number of positive protons equals to the number of negative electrons. So if we have 19 protons, we must have 19 electrons. That way the charges balance out. So the number of valence electrons in each atom affects the element's what? So a valence electron, let's say we can represent the atom. We can represent an atom like a solar system. So in the center, we got our sun, or our nucleus. And the nucleus has neutrons and protons. Now, electrons, they orbit this nucleus. Alright, so they kind of orbit this nucleus. And there's different energy levels or shells. And what happens is, the outermost electron, right, the electron furthest away from the nucleus is called the valence electron. Alright, now let's go back to our periodic table. Now you can see columns in the periodic table. There are columns in our periodic table, and they're called groups, alright? So columns in the periodic table are called groups. So this would be group 1. This would be group 2. This would be group 13. Group 13 is also called 3A. Let's write this down. Group 13 is called 3A. Group 14 is called 4A. 15 is called 5A. 6A, 7A, 8A. And it turns out that these numbers, right, this 1, 2 right here, represents the amount of valence electrons in the group. So group 1 elements, so these elements over here, all of them are going to have 1 valence electron. Alright, so Li, lithium, has 1 valence electron, sodium has 1 valence electron, and so on. Now, you can see that group 2 elements, these group 2 elements, they're going to have 2 valence electrons. So beryllium has 2 valence electrons, magnesium is going to have 2 valence electrons, and so on. And it turns out that these valence electrons affect the element's chemical properties, right? It affects their reactivity. For example, these group 1 elements, they're really reactive. In fact, if you place any of them in water, they're going to react really violently, especially as you go lower down group. These halogens over here, these things, they want to gain an electron. They're also really reactive. So you can see how the number of valence electron affects the element's chemical properties. Alright, the nucleus are classified as what? So obviously, we can see that they're the same element, right? They both have the same symbol. If they have the same symbol, they're the same element. So therefore, 2 and 4 can't be our answer because they're different elements, right? It doesn't match up. Now, one thing you gotta know is isotope. Isotopes are elements, right? That isotopes are atoms, okay? So let's say I have an atom here, right? So I have an atom here, and let's say I have another atom. Okay, so isotopes, they have the same number of protons, okay? That explains why they're the same element, right? Same element equals same number of protons. So same number of protons. Protons, but they have different number of neutrons. Different number of neutrons. Okay. So same isotopes have same number of protons but different number of neutrons. And because these atoms differ from the number of neutrons they have, they're going to have different mass numbers, right? Because remember, back to question number 1, a neutron has a mass of 1 AMU. So if you have more neutrons, right, some isotopes have more neutrons than other isotopes, and that's why some isotopes actually weigh more than other isotopes. So they're isotopes of the same element. An isomer, well, let's say I have something like this. Okay, so I'll try to draw this diagram quickly. Probably make some edits to not show you the whole drawing process. Okay, so let's say we have these two compounds. Okay, so you can see how in both of these compounds I just drew, right? Both these, we have the same number of atoms, right? We have 2 carbons, right? We have 2 carbons, we have 1 oxygen, and we have 1, 2, 3, 4, 5, 6 hydrogens, right? And there's the same amount here. So they have the same isomers, they have the same type of element and same amount of those different elements, but obviously their structure is different, right? This one, the oxygen is sort of on the outside. This one, the oxygen is kind of like in the middle. So isomers, they have the same molecular formula, but structurally, they're different. Okay, so 1 gram example of different is what? Okay, so you're saying compared to a 1 gram sample of chlorine gas, a 1 gram sample of solid aluminum at standard pressure has a lower melting point. So you're saying solid aluminum has a lower melting point than chlorine gas. Let's take a look if this is true. So aluminum, it has a okay. Wait, was it? All right, melting point. Okay. Aluminum has a melting point of 933. Chlorine has a melting point of So this answer choice is saying that aluminum has a lower melting point than chlorine, but from our periodic table, from table S, we just found out that that was not true. So you're saying that aluminum has a higher boiling point than chlorine? Let's go see. Aluminum, very high boiling point. Chlorine, not so high boiling point. So answer choice 2 is going to be our answer. Which one chemical chain? So changes. Okay, so this is something to know. Imagine if we have a water molecule. Okay. And I'm not gonna draw the lone. Actually, I am. I'm gonna draw the lone pairs. And let's say I have another water molecule. Now these two water molecules are gonna be attracted to each other. Okay. Via hydrogen bonding. Okay. So these water molecules, they have attraction to each other. Now, when I break this attraction, right, this is a physical change. Okay. So if I break attractions between two different molecules, this represents physical changes. For example, if you want to go from liquid water, to water vapor, right? So just water vapor, what you would have to do is you would have to break this attraction completely so that these water molecules just move free and turn into gas. So physical changes are represented by changes in intermolecular forces, right? If you were to break an intermolecular force, that would represent a physical change. All right. So freezing and melting. Phase changes are examples of physical changes, right? You're changing how the water looks, but you're not changing the fact that it's water, right? Melted water is still water. So this wouldn't be your answer, right? If you were to freeze water or if you were to something, melt an ice cube, for example, it's still water at the end of the day. And same for number 2, freezing and vaporization or evaporating, right? If you were to evaporate water into water vapor, it's still water. Now, let's take a look at answer choice number 4, decomposition. Decomposition is when you have a more kind of complex compound and you break it up into 2 smaller compounds. And you can see how in decomposition, the identity of your compound is different, right? You've broken up big compound into 2 smaller different things. So decomposition is an example of a chemical change. In a chemical change, you're breaking the actual bonds in the molecules, right? You're breaking the actual bonds in the molecule. But in physical changes, you're breaking the attractions between different molecules. So that's the difference, right? Intermolecular forces, they're attractions between 2 different molecules, right? Other molecules. While intramolecular forces are the bonds, right? For example, ionic bond. In this case, covalent bond, right? So that's sort of the difference. And combustion is when you are reacting something with oxygen and you're forming CO2, carbon dioxide, and water. Okay, this is combustion. And obviously, you can see how our compounds have changed, right? Your compound changes whenever a combustion reaction occurs. So decomposition and combustion reactions are examples of chemical changes. But we're looking for one physical change and one chemical change. So number 3 has to be our answer. This is a chemical change. This is a physical change. In the ground state, the atom of each element has what? That's different what? Let's look at number 1, oxidation state. Oxidation state. Alright, so we're looking at group number 2. And oxidation states are these numbers right up here. So you can see that every element has the same oxidation state in group 2. So therefore, number 1 can't be our answer. Let's take a look at number 3, number of valence electrons. Well, we can see from this diagram, right? Remember before I just said the things inside a group, right? Elements in the same group have the same number of valence electrons. And if you didn't know that, even if you didn't know that, you can look at the electron configuration. Electron configuration, if I were to draw a beryllium atom, so this atom right here, in your first shell, right, you would have 2 electrons. In your second shell, you would have 2 electrons as well. So you have 2 valence electrons, right? You have 2 valence electrons on the outermost shell. If I were to draw an atom of magnesium, right? Magnesium, here's your nucleus. You have 2 electrons in the first shell, right? 2 electrons in the first shell. Then you have 8 electrons in the second shell, right? 1, 2, 3. Just pretend I draw 8 here. And you have 2 electrons in the outermost shell, right? In the third shell, which is the furthest shell. So you can see how all these elements, right, their last digit is 2, which represents their valence electron, right? Their last digit is always 2. So elements in the same group have the same number of valence electrons, which means that number 3 is not our answer. Okay, so number 3 isn't our answer. Now let's look at number 2, first ionization energy. This looks pretty interesting. Now, what is ionization energy? Well, ionization energy, let's say we have an atom. Let's say the atom has some electrons. And this is first ionization energy. So it represents the amount of energy, right? If we have 2 electrons on this atom, how much energy would it take for me to just pull off this atom from this? How much energy would it take for me to just pull off this electron from the atom, all right? How much energy would it take for me to remove an electron from an atom? And that's ionization energy. And if we were to go to our periodic table, you'll see that for beryllium, right, things in the same group. Beryllium, element 4, ionization energy of 900. Magnesium, element 12. Oh, ionization energy is different. Oh, therefore number 2 is our answer. And it actually turns out that as you go down a group, the ionization energy for an atom actually decreases, okay? So ionization energy decreases. And all this means is that as you go down a group, the amount of energy it takes to remove an electron from the atom is decreasing, right? It's easier to remove an electron from a bigger atom. And why is that? Well, protons are in the nucleus, and they have a positive charge. So imagine I have this positive charge right here. And imagine if I have, like, let's say beryllium with only 2 shells. So you have 2 electrons here. Actually, yeah, you have 2 electrons here and 2 electrons here. And you can see how the electrons are relatively close to the nucleus, and electrons have a negative charge. So therefore, it's not really going to take that much. Compared to like other elements, it might not take that much, but if we're only focusing on group 2, beryllium actually takes the most amount of energy for you to remove the electron, right? It has the highest ionization energy in this group because the electrons are so close to this positive charge that, well, it's so attracted to it, it's going to take a lot of energy to remove an electron. And compare this to a super big atom. Compare this to atom, right? We have positive protons in the nucleus, and imagine if the atom was super big like this, right? And you have all these electrons right here, right? You have electrons all everywhere, just imagine. And therefore, right, it's going to take much less energy. It's going to take less energy for you to remove the electron, because the electron is so far away from the nucleus that it doesn't really feel that force of attraction from this positive charge. It's like two magnets, right? If you take two magnets, you put them relatively close together, it's going to like snap together, right? Imagine if one was like north and one was south. But as soon as you move as soon as you move the magnets just a little bit further away from each other, the force of attraction has gone really, really weak, okay? So as you increase the distance, you can see that the force of attraction has decreased. Which statement explains why water is classified as a compound? Imagine if you ask someone, why is water classified as a compound? And a compound, right? A compound is just when you have, right, two or more elements. In this case, water is H2O. And water has more than two elements, right? Two different elements. And the two elements are chemically combined, right? H2O looks something like this. All right, so you got two or more different elements that are chemically combined. That is what a compound is. Now, even if you don't know what a compound is, right? Just from the answer choices, it looks pretty suspicious. Because imagine if you ask someone, why is water classified as a compound? And they respond with, water's a poor conductor of electricity. Like, that does not make any sense. Or water's a liquid at room temperature. Those do not answer the question. Now, water has a fusion of this. And if you don't know what that is, let me just scroll up. So heat of fusion. So, okay, if you look here, this is just the heat of fusion. And heat of fusion, imagine if you have 1 gram of liquid water. Okay, so if you have 1 gram of liquid water, and you might be asking, well, how much energy does it take for me to evaporate 1 gram of water into water vapor, right? And the answer to your question is that it takes 334 joules per gram, right? 334 joules to raise 1 gram of water and evaporate it, okay? Now, this also does not answer the question. So answer choice 1 has to be our answer. Remember, 2 or more elements, right? 2 or more different elements chemically combined together. So water can be broken down by chemical means. This has to be the answer. Empirical formula. What's an empirical formula? Well, let me show you something. All right, my bad. So let's look at let's look at answer choice number 2. This is not an empirical formula. Now, why? Empirical formula is kind of the simplified version of a molecular formula. So it's like the simplest version of that molecular formula. And what I mean by that? Well, C2H6, you can see that 2 and 6 share a common factor of 2, right? 2 and 6 share a common factor of 2. So you can simplify this formula into C1H3, okay? Now, because this formula can be simplified, it's not an empirical formula, okay? So the question is basically asking you, which formula is in its simplest form, okay? So which formula do you not have to simplify? Do you not need to simplify? In this case, we can simplify answer choice number 3, right? They both share a common factor of 3 in the formula. So you can simplify this into C1H2, right? So this wouldn't be it, because you can still simplify this formula. Can you simplify this formula? Sure you can. Share a common factor of 2. So this would be C2H5. And because you can simplify this formula further, no. But can you simplify this one? Well, they both share a common factor of 1, but that doesn't do anything. You can't simplify this any further. Therefore, it's an empirical formula. It's in its simplest form. Which compound? Okay. Ionic bonds, usually, right, they involve a metal and a non-metal, okay? An ionic bond. And what happens is the metal gives an electron to a non-metal. Now, if you're giving a negative charge, right, electrons are negatively charged. So if a metal gives an electron, it's going to become positively charged because it lost the negative charge. And because the non-metal is accepting that electron, it's becoming more negatively charged. And opposites attract. So this positive charge is going to attract the negative charge. But it turns out that it doesn't always have to be a metal and a non-metal forming an ionic bond. And whenever you're asked this question, like which compound blah 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 contains ionic and covalent, you should be thinking of polyatomic ions. And polyatomic ions are in table E. You should be thinking about those when you're thinking about when there's a question relating to ionic and covalent bond. Now, your first step is to identify which of these elements has one of these ions, okay? That's what you're looking for first. In this case, Ki, K is an element, I is an element. It's not a polyatomic. So 1 can't be our answer. CaCO2, right? CaCO2, they're all elements, right? There's a metal and a non-metal, but there's no polyatomic. So this can't be our answer. Answer choice number 3, is there a polyatomic here? No. So answer choice 3 can't be our answer, and answer choice 4 is our answer. Might be confused about this polyatomic ion thing and why we have to search for it. Well, CN, right, it turns out CN is actually cyanide, CN minus. And it's bonded to Na. Now, Na, imagine if Na gives away an electron, right? Well, Na is going to become positively charged, all right? And if you look in your periodic table, I know this is a lot of information right now. Sorry about that. But Na wants to give away electron. And you can see right here, in your periodic table, Na likes to form ions with a +1 charge. So they like to give away 1 electron, 1 valence electron. And what happens is that Na likes to form +1 charge. Cn likes to form a -1 charge, and they create an ionic bond. So NaCN is our formula. The ionic bond comes between the Na ion and the Cn minus polyatomic ion. And you might be wondering, where's the covalent bond? Well, the covalent bond is happening between the carbon and the nitrogen, okay? So the C and the N is where the covalent bond is formed, right? So this is where the covalent bond is formed, and this whole thing is where the ionic bond is formed. All right, what occurs during this reaction? So to better understand this problem, let's draw a diagram. And okay. So you can see how in order for this reaction to occur, right? What's kind of happening in this reaction? Well, sort of, if you can think about it, if you can kind of imagine this, imagine if this bond right here, right? Because these two H atoms, they have a bond right here, a covalent bond. And what happens is this bond is breaking. Okay, so this bond is breaking, and when the bond is broken, it allows it to separate into 2 individual H atoms, which you can see on this side of the equation. Now, in order for us to break this bond, right, needs to absorb energy, right? So as bonds start to break, they're absorbing energy. So what occurs during this reaction? Well, energy is absorbed as bonds are broken. So that's going to be our answer. Heat of a reaction for a chemical change. So imagine if we have a potential energy diagram. All right, so imagine if reaction progress. And on the y-axis, you're going to have potential energy. Okay. So during a reaction, right, during a chemical reaction, you can actually measure the potential energy of your reactants, your products. You can kind of measure the potential energy throughout the whole reaction, and you can set up this graph for it. Now, this diagram, it's going to look something like this. Depending if it's releasing heat or absorbing heat, it's going to look something. All right, this is an example of a reaction where you're losing potential energy, okay? Now, the heat of a reaction is just how much has your potential energy changed from the beginning of your reaction to the end of the reaction, okay? So at the beginning of your reaction, this is the potential energy of your reactants, right, when you started. And this is the potential energy of when you ended the reaction, right? Potential energy of your products. So your change in potential energy is just going to be the potential energy of your products minus the potential energy of your reactants. Now, let's just visualize this with an example. Let's say if our initial potential energy is 100 and some unit, let's just say it's 100, and our final potential energy is 50. Well, how much has your potential energy changed? Well, obviously you decreased it by negative 50, right? It decreased by 50. And how do you find this? Well, you would take your final amount and you would subtract your initial amount. And boom, you get your heat of reaction. Okay? When chemical reaction okay. So it turns out that chemical reactions don't have to happen one way. Imagine if you have ammonia. All right. And this creates H2 and N2. All right. So ammonia can decompose to form hydrogen gas and nitrogen gas. But hydrogen gas and nitrogen gas can recombine to form ammonia. So this reaction happens in both directions, right? This can turn into this, and your products can turn back into reactants. So this is an example of a reversible reaction. All right, this is an example of a reversible reaction, a reaction that can happen both ways, basically. Now, when a chemical reaction is at equilibrium, what you need to know is that the rates of the reactions are equal. So the rate which this turns into this is equal to the rate which this turns into this. So let's say, to better understand, let's say I'm going to use okay, so let's say we have 3 circles, and we have another 3 circles here on the other side. Now, every second, all right, so every second, one circle from this pile goes to the other pile, and the one circle from this pile goes to the initial pile. And what's going to start to happen is you can see how the rates of this circle going from here is equal, right? Every second, one circle from this part is going to there, and one circle from this part is going to here, right? The rates are the same. So if you continue this process, right, on and on and on, right? If you continue this process on and on and on, you can see how the amount of circles we have doesn't change, right? Because the rates of our, in this case, reaction, right? We're kind of doing a reaction kind of example thing here. You can see how if the rates of our reactions are equal, right, then our amount of circles we have in each pile remain the same. And in chemistry, we say that the concentration of each reactant and the concentration of each product must be constant. All right. The concentrations must be constant. So one ball goes here, one ball goes here, and then the concentrations, they remain constant. In this case, the amount remains constant. Now, a lot of people, what they get confused is that they think that the concentration of reactants and concentrations of products, they are equal. And this doesn't have to be. All right. Sometimes, right, if we're going back to this example, sometimes there can be 4 balls on one side, or 4 circles on one side, and 3 circles on the other side. And one ball goes this side, one ball from here goes to this side, and you can see how over time, right, the amount of balls we have are the same. I mean, amount of balls aren't the same, but they're constant, right? They're constant. All right. So which element is present in organic compounds? It's probably at least like this question appears basically in every Regents. It's always carbon. Chemistry, you're gonna learn about just like just a little bit of Chem, and organic chemistry studies carbon-based compounds. 2 types of organic reactions. This one, this is just a memorization problem. So if you don't know this, well, just skip it during the test and hopefully you'll remember it like a couple minutes later. Deposition is when you're going from a gas back to a solid. But this isn't an organic reaction, so this can't be it. All right, we have deposition again, so this can't be our answer, right? Now, let's look at this one. Polymerization. Now, you might have learned of polymers in biology. Imagine if you have like small molecules, right? And imagine if you have a bunch of these small molecules. And what they do is they kind of chain together to form this one bigger molecule, all right? So this bigger molecule is kind of made of these smaller molecules kind of copy and pasted everywhere. So that's polymerization. When one small molecule, you get a whole bunch of those small molecules, and you can make a big molecule, all right? Really big one. So transmutation, this is an organic reaction, polymerization, but transmutation is not an organic reaction. Transmutation is when you go from one element and you can actually transform it, right? Therefore, you got the trans part, and you can transform it to another element. That's transmutation, but that's not an organic reaction. So number 3 has to be our answer. Saponification is the process of making soap, and that is an organic reaction. What particles are transferred in this reaction? Well, we can see that aluminum has gone from a charge of 0, right? Aluminum has a charge of 0, right? An element by itself has an oxidation state of 0. And you can see how aluminum went from 0 to 3 plus. And you can see how Cu went from 2 plus to an oxidation number of 0. Okay? Now, changes in oxidation numbers in a reaction, these are something called redox reactions. And they involve the transfers of electrons. And even if you don't know this, from the reaction, you can see that aluminum, right, goes to aluminum with a 3 plus charge. Now, what must aluminum be giving away to form a positive charge, right? If you want to form a positive charge, well, you're going to have to kind of chuck out some negative charges, all right? And these negative charges are actually getting reabsorbed by the copper atom, which is why it went from a positive charge to a neutral charge, right? If you're trying to neutralize a positive charge, you must be gaining a negative charge. And in this case, this negative charge is actually from the aluminum. The aluminum is giving away electrons to copper, which copper accepts. In an operating voltaic cell, reduction happens in where? First of all, what is a voltaic cell? Well, let me show you. You all ever wonder how light bulbs work? How you produce electricity? And voltaic cells, you start out with 2 half cells. Half cells are just beakers. Half cells are just beakers, to kind of simplify this, with electrodes in them. So beakers with pieces of metal in them, okay? you have a wire connecting these metals, and this wire in the center usually has something like a light bulb or something, or a voltmeter in the center. You have a salt bridge. Well, I'm not going to include salt bridge, just to kind of simplify things. And you have some ions in the water, okay? So imagine if you have water in both of these containers, both of these half cells, and in the water, there are some ions, okay? And what happens is, let's say this is metal A. Let's call this metal A. And let's call the other metal B. Let's say metal B, right? It wants some electrons. It really wants electrons. So metal A is like, okay, I'll give you some electrons. So electrons will travel through the wire, right? Because metal A is willingly to give up electrons, right? This metal is willingly to give up these electrons. And these moving electrons cause electricity, which can power up your light bulb. That's the general idea of it. Then what happens is that these ions in the water, they gain these electrons. And what happens is this ion actually plates back, right? It gains the electron and it plates back onto its electrode. Well, this electrode right here, right? Imagine if you have all these tiny metal atoms, right? All right, you have all these tiny metal atoms. If a metal atom gives away an electron, it's not a metal atom anymore. It's a metal ion. And ions, they're gonna these ions are gonna dissolve in the water, okay? So I'm just gonna be clear about this. Solid metal ain't gonna dissolve in water. But as soon as a metal atom gives away one of its electrons to travel through the wire, well, this metal atom is gonna turn into a metal ion, and therefore it's kind of gonna drop in the water and kind of dissolve in it. So over time, you'll actually see that this piece of metal will get smaller, while this piece of metal is getting bigger. Now, the thing that's gaining electrons, you say that that thing is being reduced. All right. Well, the thing that's losing electrons, right? Solid metal A is giving away electrons or losing electrons. That thing is being oxidized. And the thing that you call the electrode on the oxidized part, right? Because we know that this piece of metal is, right, these metal atoms are getting oxidized on this electrode. And this electrode on the oxidized part, that's going to be called the anode. And the electrode that's on the reduced side, that's going to be called the cathode, okay? So where reduction happens, you got the cathode. And where oxidation happens, you got the anode. And a good way to remember this is anox, red cat. Anode. All right. So anode. Okay. So anode is where oxidation occurs, and reduction happens in the cathode. All right, so anode is where oxidation happens. Reduction is where reduction takes hold in the cathode. And that's how you kind of remember it. So going back to our question, in a functioning voltaic cell, reduction occurs, well, anox, red, cat. Boom. What type of sun? Yeah, this one's also just a memorization problem. An arrhenius acid is a substance, right? Let's say we have your stomach acid, HCl. If you dissolve this in water, what happens is it actually produces H plus ions. All right, it produces H plus ions and it produces CO minus ions. Now, something is considered an arrhenius acid if it produces H plus ions when you dissolve it in water. Therefore, number one's our answer because it yields H plus ions when you dissolve it in water. Phenolphthalein is pink in an aqueous solution. What? Okay, this one's all about how to read indicators, and you don't know what's right here, table M. And indicators are used for titrations. Now, there's probably going to be a problem on titrations later, so I'll probably explain that there. Right now, you have, let's say we're looking at methyl orange, okay? What this means, this pH range thing, what it means is that and in this pH, this color, right, this methyl orange is actually going to change color from red to yellow. Okay, so that's what the approximate pH range for color change. It's kind of like, you can kind of assume that from the name. And you add indicators to solutions, okay? So you actually add indicators to solution. Now, if we're adding methyl orange, let's say that methyl orange starts out red. So let's say methyl orange starts out red. Now, anything below a pH of 3.1, you're going to be red. And anything above a pH of 4.4, the solution is going to be yellow. Okay? That's kind of how you read it. For example, bromithimal blue. Anything below a pH of 6, your solution is going to be yellow. Anything above a pH of 7.6, your solution is going to be blue. All right? And you might be wondering, what happens if I have a pH like 6.8, directly in the middle, right? I'm in the middle of this pH changing color. This color changing range. And my answer to that question is, it's just going to be a mixture of yellow and blue, which is green. All right? So it's going to have some of both in there. Now, phenolphthalein is going to be pink when it has a pH above 9, and it's going to be colorless when it has a pH below 8. Now, you're looking for phenolphthalein when it's pink. So phenolphthalein is pink when you're above a pH of 9, which means that what number here is above 9? 14. NH3. So also this one you kind of have to memorize. Instead of arrhenius acids, right? Arrhenius acids, arrhenius bases, we're looking at Bronsted-Lowry acids and Bronsted-Lowry bases. Now, Arrhenius acids, okay? Actually, Arrhenius bases, all right? So, Arrhenius, I don't even know how to spell his name. Bases, all right? Arrhenius bases are just something where if you put it in water, for example, something where if you put that thing in water, for example, NaOH, put it in water, it's going to disassociate into OH minus ions, okay? It's going to disassociate into OH minus ions. All right, so that's a definition of an Arrhenius base, all right? Something that has OH in its formula, and when you put it in water, it produces OH minus ions. Now, the reason why this kind of definition might be a little bit outdated is because you have something like ammonia that doesn't have OH in its formula, but it's still a base. So therefore, people actually created a new definition. This is called Bronsted-Lowry definition of a base. The Bronsted-Lowry definition of the base is just a proton. It's a proton acceptor. And a proton is the same thing as a H plus ion. Now, some people get confused about this part. A neutral hydrogen atom, all right, a neutral hydrogen atom has one proton. So imagine you have one proton in your nucleus, and it has one electron. All right, so this is your one electron. It's not drawn to scale, obviously. Actually, I'll make it sort of to scale. Now, imagine if you lose this electron. Well, you're losing a negative charge, so it's just going to be one proton in the nucleus. And this is the same thing as H plus because this is a hydrogen atom, right? This right here is a hydrogen atom. And when a hydrogen atom loses an electron, it becomes a hydrogen ion, hydrogen cation, which is just a proton. So this is going to be a sepsa H plus ion. That's a definition of an Bronsted-Lowry base. It's a proton or H plus acceptor. And something really cool is, imagine if NH3 gained a proton or H plus ion. This is going to become NH4 plus, right? You gained an addition of a hydrogen, right? You gained an extra hydrogen, and you gained a charge. And guess what? NH4 plus, just go to your periodic table, not your periodic table, you go to your reference guide, boom. This is something actually called ammonium, all right? So that's pretty cool. Okay, next. Which reaction releases the greatest amount of energy per mole of reactant? Okay. Which reaction releases the greatest amount of energy per mole of reactant? All right. Let's take a look at answer choice number 4. This stuff, all right, if you didn't know, fission reactions, they're the things in nuclear power plants. All right, you know those big nuclear power plants generating a lot of energy? This is the reaction that's going on. The stuff in your atomic bomb. Why did I say your atomic bombs? Just the stuff in an atomic bomb, right? Fission is the reaction that happens in an atomic bomb. And fission releases a huge amount of energy. All right, a huge amount of energy. None of these things even come close to the amount of energy released. And that's because in fission reactions, mass is being converted to energy, all right? Mass is being converted into energy. And, y'all know from Albert Einstein equation, E equals mc squared. Even if you have a little bit of mass, you're going to have a large amount of energy because you got the c squared part, if you know what I'm saying. All right? And c, this represents the speed of light. So you have a little mass, well, you're taking the speed of light and you're raising it to the second power. So yeah, that's going to be a lot of energy. The only reaction that releases more energy than this is a fusion reaction. And this occurs in the sun. Which nuclear is negatively charged? A beta particle, a positron, a neutron, an alpha particle. Now, if you don't know this, scroll right here. Which one is negatively charged? All right, let's take a look. Is a neutron negatively charged? Nope. Is a positron negatively charged? Nope, it's positively charged, actually. So it's not negatively charged. Is an alpha particle positively charged? Nope. It's actually positively charged, so no. So a beta particle is negatively charged. And a beta particle is just an electron. All right. So which electron configuration represents an atom of chlorine and in an excited state? Now, atoms, they reach an excited state when, let's say, if you have an atom, right? And let's say it had an electron. When an electron moves from one energy level to a higher energy level, right? A higher shell, right? Or you can think about it as when an electron gets further away from the nucleus, well, it gains energy, all right? And you say that the electron is in an excited state. So when it moves from one shell to a higher level shell, you say that the atom's in an excited state. And electrons actually, they can go back to their energy states and they release the energy as light. Now, chlorine, if you scroll to your periodic table, this has, let's go here, chlorine, it has an electron configuration of 287. So this means that if you have an atom of chlorine, in your first shell you have 2 electrons. That's where the 2 comes from. Second shell you have 8 electrons. Second shell you have 8 electrons. 2, 3, 4, 5, 6, 7, 8. And in your third shell, you're going to have 7 electrons. Now, I can't fit the whole thing, but imagine if chlorine's in an excited state, okay? Imagine if one of the electrons from the second shell goes to the third shell, all right? So then the new electron configuration will be 2, 7, 8, right? One electron from the second shell goes to the third shell. So the amount of electrons on the second shell decreased by 1, and the amount of electron increased by 1 in the third shell. And, well, which one is it? Well, 2, 7, 8, number 2. Boom, that's our answer. And another way to check your answer is, in an atom of chlorine, you have 17 electrons. So in your answer choice, the amount of electrons has to add up to 17. In this case, you can immediately remove this answer and this answer. So just by doing this, 50-50. All right. Which amount? Okay. So you're actually going to have to score the table I in that problem. I'm just going to make my periodic table. I'm just going to scroll up. Okay. Now, what is the net amount of energy released when 1 mole of H2O liquid is produced? Now, let's take a look at this reaction. All right, and let's see if we can find it somewhere. Oh, we found it. Boom. Found this energy, and it turns out that this reaction releases this much amount of energy. All right, so this is the delta H value, and the delta H value is the same thing as heat of reaction. So this is how much energy, basically in the context of this reaction, how much energy have you released? And in this case, you have released 571.6 kilojoules of energy. All right. And the way you know that something's releasing energy is if, right, a minus sign. If you have a minus sign, you're releasing energy. Well, if you have a positive sign, you're absorbing energy. Now, if you go back here, all right, remember the amount of energy we released is 571.6 kilojoules. All right, that's how much energy we released. Now, in the reaction, you can see that for every 2 moles of H2O that's produced, we release this much energy. But if we produced 1 mole of H2O, right, if we produce half as much as water, we're going to expect half as much heat released. So it's going to be half of this, which is going to be 285. All right. So just to recap, right? So for every 2 moles, you release this much energy. If you cut the amount of water you're producing by half, you expect the amount of energy you release by half. Okay? So if one thing doubles, other thing doubles. If one thing gets cut in half, the other thing gets cut in half. Element X reacts with copper to form the compounds blah blah blah. Well, copper, if you go in your periodic table, copper actually forms 2 charges. All right, it actually has 2 oxidation states. Copper can form a +1 charge or a +2 charge. All right, so copper can form a +1 charge and a +2 charge, meaning that copper likes to give away an electron or likes to give away 2 electrons. All right. Now you can see that it forms the compound CuX and CuX2. So this X right here, right? This X must have a -1 charge. And how do I know this? Well, if I have something, right, let's say I'm pairing Cu plus 1 with X that has a -1 charge, well, if you do crisscross, you're going to get Cux. All right. So the oxidation number of your element becomes the subscript of your other element, while the oxidation number of your copper is going to be the subscript of your other element. Now imagine if we did this reaction for C2X minus 1 and do crisscross. The oxidation number of X, right, is going to become Cu's subscript, all right, the amount of copper there is. While the amount of copper, the copper's oxidation number is going to become the amount of X there is in the formula, right? This 2 becomes the X subscript. So you can see how when the X has a -1 charge, it produces these formulas. So if you scroll in your periodic table, which elements produce a -1 charge? Oh, group 17 elements. And you know that the charge, right? You might be thinking, why can't it be +1? Well, this is because usually metals, right? Metals can't form ionic compounds, right? This right here is an ionic compound, right? It's when you have a cation, right? Something that wants to lose electrons and something that wants to gain electrons, right? Something that wants to gain electrons. The thing that wants to lose electrons, well, if you're losing a negative charge, it's going to become positive. While if you're gaining electrons, that thing is going to become negative. So therefore, you must have one positive charge and one negative charge in an ionic compound. What is the mass of 1.5 moles of CO2? Now we're going to use something called the molar mass. So you have 1.5 moles of CO2. All right. And what you're going to do is you're going to set up dimensional analysis, and you're going to say that for every 1 mole of CO2, and then you're going to have to find the molar mass of this. So basically, the molar mass of a compound, in this case, is just how many grams of CO2 do you have for every 1 mole, all right? So for every 1 mole of CO2, how much does it weigh in grams? In this case, you go to your periodic table, and you're going to, all right, so we have CO2. And you're going to take a look at the atomic mass of carbon, the atomic mass of carbon. All right, so we have the atomic mass of carbon. You're going to take the atomic mass of that element and add it to the atomic mass of the other elements. So atomic mass of oxygen, that's just going to be 16. But because we have 2 oxygens, it's going to be 16 times 2. Add this all up. All right, so that's going to be 32. That's going to be 44.01. And that's how much your CO2 weighs for every 1 mole. All right, so for every 1 mole of CO2, it actually weighs 44.01 grams. All right, it's just the atomic it's just the atomic mass of each element added up. That's going to be your molar mass. So 44.01 grams. Your units cancel out, and putting this into your calculator, you're going to get about 66 grams. All right, so it's just a matter of canceling out units, all right? If you're not familiar with canceling out units, a simpler problem might show you what I mean. So imagine if we have 24 cookies, all right, and we want to find out how many dozen is 24 cookies, right? How many dozen is 24 cookies? So you're going to say for every 1 dozen, right, there's 12 cookies. And you're going to see how the units cancel out. So you're going to get 2 dozen as your answer, right? This is all about canceling out your units, all right? So that's just kind of that's just kind of like a basic example of that. Which type of reaction is represented by this? Okay, so you can see how this K, right, swapped with the Cl, right? This K went to the Cl. And you can see how the Ba went to the CO3, right? They kind of swapped partners, if you will. So this is an example of a double replacement reaction, right? You're replacing the Ba with the K, and you're replacing, right? Replacing this with this, and you're replacing this with this. Okay? So that's going to be double replacement. All right. Synthesis is when you're just taking two, can be atoms, elements, and you're merging them into a bigger compound. Decomposition is the opposite of this. When you got a big compound and you're breaking it up into two smaller, could be atoms, elements. All right. Just the big thing breaks up into two smaller things. And single replacement is when you have, let's say, A plus AB plus C, and this thing kind of kicks out A and it swaps with it. So it becomes CB plus A. All right. So it's just when this thing swaps with one of this thing. Which sample dissolved in 1 liter of water produces the solution with the highest boiling point? Okay. This is something. Alright, this boiling point. Okay. So one thing to know is that all atoms, alright, molecules, in this case we're talking about water, okay, because we're talking about a solution, right? Our problem is talking about in 1 liter of water. When we're talking about water, let's say, water molecules can get attracted to other water molecules, okay? Alright, so oxygen kind of likes to hog electrons. It likes electrons around it, alright? So it has a partial negative charge, right? Because it likes to hog electrons, and electrons are negatively charged. While hydrogen, it kind of got its electrons stolen, so it's going to have a partial positive charge. And yeah, this happens in every water atom molecule. And what happens is opposites attract. So this negative charge gets attracted to partial positive charge, and boom. And this is called an intermolecular force. So this is just a force of attraction between two different molecules, okay? Now, this is actually something called a hydrogen bond, okay? It's something called a hydrogen bond. Hydrogen bonds are really strong intermolecular force. Now, let's say if we add an ion. So, let's say Na+. We add ions to the solution. And obviously, this positive charge will get attracted to this negative charge. And it turns out that when you add ions to a solution, the attraction the ion has on the molecule is stronger than the attractions between the water molecules itself. This is called an ion dipole force. All right. And this thing is stronger than the hydrogen bond, okay? So basically, when you add ions to the solution, the forces of attraction between the ion and the water is stronger than the attraction between a water molecule and another water molecule. And what happens is, because these attractions are stronger, well, you're going to take more heat. You're going to need more heat to break this force of attraction in order to turn into, let's say, from a liquid to a gas, right? Because when you're going from a liquid to a gas, you have to break these forces of attractions. But if these forces of attractions are stronger, you're going to need more heat. So therefore, the boiling point of your substance will increase as you add more ions. All right. Now, let's take a look at this. So the more ions you have, the higher the boiling point, which means 1 and 3 can't be our answer, right? They don't have as much ions. Now, imagine if you dissolve magnesium chloride in water. What happens is you're going to get magnesium, a magnesium ion, and you're actually going to get 2 chloride ions. And this 2 comes from this equation right here. You're going to get 2 chloride ions. So you're going to get 3 ions in total, or 3 moles of ions in total. While if you dissolve Ki in water, you're only going to get 2 ions in water. Okay? You're only going to get 2 ions in water. And the more ions you have, the higher the boiling point. So because this produces the most ions, well, number 4 is our answer. So given the balanced equation represented. Okay. So you can see how when there's 4 moles of NH3, you're gonna produce 6 moles of water, which means if you have 2 moles of NH3, you're gonna have half the amount of water produced. So you're gonna have 3 moles of water. Volume change to okay. So pressure, volume. Okay. So you're gonna have to use a formula for this problem. This formula is called the combined gas law, and you can actually find it in your reference guide. It's gonna be here, combined gas law. All right, and these are all your units, and you can pause the video there, by the way, if you don't know. All right, so you have your temperature, 300 degrees Kelvin. You have your pressure, you have your volume. So the formula is formula before, you're going to use that. So it's P1 times V1. So our P1, our pressure of our first thing, that's going to be 240 kilopascals. I'm not going to write the units because I'm lazy. Times our volume, 70 milliliters, over the temperature, 300 degrees Kelvin, equals to this is going to be equal to the temperature. All right, we have the temperature here, times the pressure, and then in this case we're trying to solve for volume, so we're going to call this X. Okay, so we set up an equation. Now we just have to solve it. So also, y'all got a calculator in the Chem Regents, and I actually have a really cool trick with the calculator. All right, and this is probably going to save your life. Okay, it's a crazy hack. It's a crazy hack. So wait, hold on. So divided by 300 times 60. Okay. Wait, 300 degrees Kelvin. I'm just gonna get my calculator out real quick. Okay, so okay. 70. And you're gonna get 52.5 milliliters. Now here's the cool calculator trick I was talking about. Okay, so if you take a look here, right? All right, you're gonna go to apps. All right, you're gonna go to apps, this button right here, and you're gonna scroll down, and you're gonna go to SciTools. Okay, so if you scroll down a bit, you're gonna see SciTools, and you're gonna press on that, press enter, and now guess what? You got a SIGDIG calculator, so you don't gotta struggle on any problems, right? You could do 9 plus 3.2 times 6, right? You can do all of these calculations, and guess what? Press enter, it rounds to the correct sig digs. It's pretty cool. So yeah, if you ever got a sig dig problem, yo, just use your calculator. All right, 100. I'm probably gonna make a cut after I do problem number 42. It's getting late. All right, 100-gram sample of H2O toying. This will be the final temperature of water. So this is a problem where you have to use this formula. This Q equals MCAT. All right, Q equals MC delta T. All right, and what this formula is used for is let me just find the space where I can. Let me just find a space where I can show this example. Okay, so let's say if we have 50 grams of water and we raise the temperature of the water by 23 degrees Celsius, and we want to find out how much heat does it take, how much heat does it take to do this? And you're going to use this formula, Q equals MCAT, all right? Where Q is the amount of heat. Q is the amount of heat. In this case, 8,360, so let's substitute that in. You have M, that's the mass of your whatever you have, 100 gram. All right, let's go. Then you have your C. C is the specific heat capacity of water. And you can scroll up here. Water has a specific heat capacity of 4.18 joules times. Where is my work? Right here. Times 4.184. 4.18. I'm not going to write actually I am going to write the units out. Times Celsius. And times your change in temperature. That's delta T. Now, your initial amount of temperature is 22.0 degrees Celsius, but you're trying to solve for the final temperature of water. And delta T is equal to the final temperature of the water minus the initial temperature of the water. So you have your initial temperature of the water, which is 22 degrees Celsius, but you're trying to solve for the final value. And now all of this is just calculator work. All right. All of this is just calculator work. Times 20 plus 22. I got 42 for this one. Let's see if it matches up. Oh, let's go. Which compound has the strongest hydrogen bonding at STP? So hydrogen bonding is just when this is an intermolecular force, and we talked about intermolecular force, right? And we said that H2O has hydrogen bonding. And then hydrogen bonding is just when you have oxygen, right? Oxygen really loves electrons. So it's going to have a really strong partial negative charge. While hydrogen is going to have a really strong partial positive charge. All right. And when you have hydrogen bonded to either fluorine, nitrogen, or oxygen, that's an example of a hydrogen bond. So H2O is going to have the strongest hydrogen bonding because all of these atoms, they don't have fluorine, nitrogen, and oxygen. Only the first answer has the hydrogen bonded to any of these elements. Okay, so let's see. Does our hydrocarbon follow CN H2N plus 1? All right, plus 2. Does our hydrocarbon follow this formula? If it does, then we know it can't be an answer because we're looking for an unsaturated hydrocarbon. The only types of hydrocarbons that be saturated that are in our reference guide is an alkane, and this is the formula for the alkane. So we're trying to look for something that's not following this formula. If we plug in 4 in answer choice 3, you're going to get C4, and then you plug in 4 for the N in this one, you get C4H10. So this hydrocarbon does follow this formula, which means that this can't be your answer. Let's look at C2H4. Well, does it follow this formula? If you plug in 2, right, you're going to get C2. And when you plug in 2 right here, you're going to get H6. Oh, it doesn't follow this formula. Therefore, 1 is our answer, right? Because this isn't an alkane. It doesn't follow this formula. And if you draw this out, it'll look something like this. So you have something like this. This is how it looks like, okay? So you have 4 hydrogen atoms and you have 2 carbon atoms, and it has a double bond, okay? Which radioisotope is used in dating geological formations? This one's purely memorization, okay? Answer choice is 2. Uranium is used to date rocks, all right? Measuring the ratio between uranium 238 and lead 206. This allows you to find out, this is used for dating geological formations, dating like rocks, for example. There are a couple isotopes you need to know, you got to memorize, and you got to know what they're used for. Iodine-131 is used to check if your thyroid is healthy or not. You also have carbon-14 dating, and carbon-14 is used to find out when an animal has died. You have radium-226. This is used for cancer therapy. And cobalt-60 has 2 uses. It's used in cancer therapy, but it's also used to extend shelf life, okay? So food irradiation. That's all you've got to know for that. Point. Which sample describes the energy of the particles in the interval dE? So here. Well, obviously, from the graph, even if you don't know what a heating curve is, if you look at dE, you'll know that the temperature right here is staying the same. It's staying constant. So therefore, because our temperature stays the same, right, the average kinetic energy is the same, right? Our particles are pretty much going to move the same speed from this point to this point. So we know that answer choice number 1 and answer choice number 2 and answer choice number 4 can't be our answer, because obviously from this graph right here, the kinetic energy, average kinetic energy, stays the same, and the only answer choice left you have is number 3. Now, it's important to understand what's going on in a heating curve, right? So imagine if this was a heating curve for water. Now, water, right, we know that water has pretty strong intermolecular forces of attraction between 2 water molecules in this case. All right. Now, when water is a solid, right, imagine if we have solid water here, so ice, right? And solid water, imagine if we're heating this up. So I'm just going to draw a red line to show the intermolecular force between these 2 water molecules. And let's say we have this piece of ice, we're heating it up, right? So the temperature is increasing, we're heating it up. And all of a sudden, all right, when we're going from B to C, so this part right here, you're going from a solid to a liquid, okay? So whenever you have a straight line in your heating curve, it represents a phase change, okay? So in this case, DE represents when you're going from a liquid to a gas. BC represents when you're going from a solid to a liquid. Now, because our temperature stays constant, we know that the energy, right, what we're essentially doing is, well, we're trying to weaken these intermolecular forces, right? So during this BC interval, what we're doing is we're weakening forces of attraction between 2 different water molecules. And when we weaken them, this allows them to kind of slip and slide past one another, becoming a liquid, okay? So this is how you go from a solid to a liquid. You weaken these intermolecular forces. That allows the molecules to kind of slip past one another. And when you're going from a liquid to a gas, what you're essentially doing is you're completely breaking these intermolecular forces, okay? So you're completely getting rid of them, all right? You're completely getting rid of them. So let me just erase this. So now they don't have any attractions between one another, and therefore they can flow into the gas phase, right? They can go everywhere. So that's kind of the summary, okay? So when you're going from a solid to liquid, you're weakening intermolecular forces, and when you're going from a liquid to a gas, you're completely breaking the intermolecular forces. Potential energy diagram, which... So in order for a chemical reaction to happen, first of all, particles have to hit each other, okay? Particles have to hit each other in order for a reaction to happen, okay? Now, the second thing you need is for the particles to be in the correct orientation. So they got to hit the right way. And what do I mean by that? Let's say if I have atom A reacting with molecule BC to produce AC plus B. All right, and let's draw a visual representation of this. So let's say I have atom A, and it has to collide, right? It has to hit molecule BC. Now, will this reaction work if the A part of the A atom hits the B part of the molecule, right? Will this happen? And the answer is no, okay? So if atom A hits the B part of BC molecule, this reaction is not going to occur because atom A wants to react with the C part of the molecule. So therefore, right, yeah, you have to swap these positions, right? So the A has to hit the C part of the molecule in order for the reaction to occur, not the B part. And that's what I mean by they have to hit the right way, have to hit in the correct orientation. And finally, particles, they have to hit each other with enough energy, okay? So those are the three things that you need for a chemical reaction to occur. Now, right, what a catalyst does, you might have learned this in biology, but it speeds up a chemical reaction, or it increases the rate of an reaction. And does this by, you can sort of think about it as it arranges your particles, your molecule, in the correct orientation, and it lowers the amount of energy you need to initiate the reaction, which is also called the activation energy. Okay, so you're lowering the activation energy, and you're orienting the molecules, in this case, in the correct way. Now, this is a potential energy diagram, and you'll see that you have this little hill right here. What does this hill represent? Well, from this point, right, from the top of this hill to right here, right, so we're talking about arrow number 1. Arrow number 1 represents the activation energy for the forward reaction. And so this means that if you're trying to go from reactants to products, your particles have to collide with this much energy. So this much energy in order for the reaction to occur. Okay? So you have to collide with this threshold. You have to meet this threshold of energy for the reaction to occur. And what a catalyst does, it lowers that energy. So it lowers the energy threshold. So you can imagine if you add a catalyst, right, the potential energy, the amount of energy needed to start the reaction is going to decrease, right? If I just erase this so you'll see it better, you can see how before the addition of a catalyst, you need quite a lot of energy to start the reaction. But when you add a catalyst, this amount of energy decreases. Therefore, it speeds up this reaction. And what happens is you can see that arrow 1, right? Obviously, this arrow is affected by the addition of a catalyst. And also, this arrow right here, arrow number 3, is affected by the addition of a catalyst. And arrow number 3 is the transition state. It represents the transition state. Arrow number 1 represents the activation energy, which decreases. And arrow number 3 represents the transition state, which is when the particles, right, when you're transitioning from the reactants to the products, okay? Let's see here. Which balance equation represents a redox reaction? So whenever you got a question like this, you got to assign oxidation numbers. Now, an element by itself, okay, an element by itself in its natural state has an oxidation number of 0. So magnesium, right, it's by itself. It's not bonded with anything. It has an oxidation number of 0. Chlorine, also, in its natural state, it exists as CO2. So its oxidation number is 0. And I deleted all the annotations here, so you're not going to see them, but you have something called diatomics. So diatomics. Diatomics are atoms that, when they exist in its natural state, right? For example, hydrogen gas. Hydrogen, right, in its natural state is actually bonded to another hydrogen. All right, so that's a diatomic. So it's just an atom bonded to the same atom. Okay. For example, oxygen as well. Oxygen in its natural state exists as oxygen gas, and it looks something like this, right? And you have the lone pairs. Oxygen looks something like, why did I draw that many lone pairs? So something like this, right? This is oxygen. So you can see how diatomics, they're just two of the same atoms bonded together. And there are 7 diatomics you gotta know. And how I remember it is have no fear of ice cold beer. Okay? Why did I say beer? Beer. Okay? Have, this represents hydrogen. Have this hydrogen. This represents hydrogen. Alright, no, this represents nitrogen. Why is this keyboard messed up? I have no fear. Nitrogen. Fear, this represents fluorine. Let's spell this. Of, this represents oxygen. Ice, this represents iodine. Sorry, this is taking a long time. Whoa. Okay. Have, what the hell? What is going on? Oh. Okay. Well, that was a little bit weird. Okay. Anyways, so the thing I like to remember, all right, is have no fear of ice cold beer. Have, right, no fear of ice cold beer. Okay? So have no fear of ice cold beer. And you can see how the beginning of those words, right, they match up with the element symbol. Okay? And you can also remember the diatomics as heavenly 7. So this one, heavenly 7. All right, you can see how the heavenly, that comes from the hydrogen part, right? And 7, because, well, these things form a 7 shape, these diatomics, right? And you have to remember these, okay? So these are just diatomics. They're the same atom, right? Just bonded to itself. Atom bonded to itself in its natural state. So, yeah. Now that I got that out of the way, magnesium, right? If you look in the periodic table, magnesium likes to form a 2 plus charge. It always forms a plus 2 charge when it's bonded to another atom. So as a plus 2 charge. And chlorine, well, it has multiple oxidation numbers. Right, let me just erase this. Chlorine, chlorine has multiple oxidation numbers, as you can see. So we have to solve for the oxidation number of chlorine. Let's call the oxidation number X. Now we have 2 chlorines, so let's write 2X. And then plus 2, right, because magnesium's oxidation state is plus 2. And you're going to set this equal to 0. All right, so the charge of the magnesium plus the charge of the chlorine is equal to 0 because the whole compound by itself is neutral. So the charges must balance out. And solving for X, you're going to get X equals -1. And this is a redox reaction, right? Magnesium went from 0 to plus 2. Chlorine went from 0 to -1. All right. pH of a solution of an acid. All right. So 7 here. And things that are acidic are right here. I'm just going to write acid. And things that are basic are here. Okay. Acidic, 14. You have 1. All right, so things that are acidic are lower on the pH scale than things that are basic, which is higher on the pH scale. Now, when you're adding acid, the hydronium ion concentration becomes 100 times greater. So what you need to understand is that, let's say if we have something with a pH of 6, and let's say if we have something with a pH of 7, what you can say is that, the thing with the pH of 6 is 10 times more acidic. All right. So let me just put this. Okay. So that's what you got to understand. You can say that the thing with the pH of 6 is 10 times more acidic than the thing with a pH of 7, meaning that a jump down on the pH scale is a 10 times increase in acidity or hydronium ion concentration. So when you're going from a jump from 7 to 6, right, it's a 10 times increase in acidity. If you're going from 6 to 5, it's a 10 times increase in acidity. So if you're going from 7 to 5, it's 100 times increase in your acidity, which is, right, it matches what we're looking for in the question. So our answer choice is 5, right? We started from 7, and our thing became 100 times more acidic. So we're going to jump 1 down, that's 10 times, another down, 10 times 10, 100 times greater. All right, now I can delete this. Okay. A chemical name for this compound is what? Now you have to identify the functional group. And okay. Okay. So turns out I wasn't sharing my screen in this part, but if you started out from a pH of 7, well, if you're going down on the pH scale, you're becoming more and more acidic. And it turns out that a jump from the pH scale, right? Let's say if we were going from a jump from 7 to 6, and then from 6 to 5. Well, each jump is an increase by 10 in acidity. All right, so this is a 10 times increase, this is a 10 times increase. So if you're going from 7 to 5, 10 times 10 is 100, which is why our answer is 5. 47. So given the formula for a compound, a chemical name for this compound. So first thing you got to do is identify this functional group. So this functional group looks something like this. So what's weird about this molecule is that you have this carbon double bonded to oxygen, and then you have like 2 more carbon chains. All right, you have a carbon double bonded to oxygen, and you just have like 2 more carbon chains surrounding it. Let's call those carbon chains R, right? It can be any length. And if we go here, well, which one of these functional groups matches my diagram, right? So Oh, it's a ketone, right? Right. You have an oxygen bonded to a carbon, and you have just two functional, and then you have two carbon chains, right, surrounding that functional group. You can kind of think about it like this. Now, the first step to naming this compound, well, identifying the longest carbon chain, right? You have 4 carbons in a row. So therefore, you're going to use the prefix but, right? You have 4 carbons in a row. And if you didn't have this functional group and you just had 2 hydrogens, right? If you just had 2 hydrogens and you didn't have this oxygen right here, this would actually be called butane. But because our functional group is a ketone, all ketones end in none, right? Own. So what you're going to do is you're going to drop the E and you're going to add 1 to the end. So this is going to be butane, which is answer choice number 3. What occurs in fission and fusion reactions? Well, it's just that small amounts of matter are converted into large amounts of energy, right? That's what's happening in fission and fusion reactions, right? You have a little mass, but with that little mass, you're able to convert it into large amounts of energy. Fission's what happens in bombs, atomic bombs. So to balance out this reaction, all you got to do is make sure that the stuff on the top on this side equals to the stuff on the top on this side. And you have to make sure the stuff on the bottom on this side matches up with the stuff on the bottom on this side. So let's say element X has a atomic mass of Y and Z. All right, so I'm just gonna write this in AZX notation. Okay, you have your symbol, element symbol. We don't know what that is. We don't know the atomic mass, and we don't know the atomic number. Now we know that the stuff on this side has to match up with the stuff on this side, right? We know that 13 plus 2, right, that's the stuff on the left side, has to equal to 0 plus Z. Therefore, Z has to be 15. So our atomic mass is 15. And element 15, let's go here. Element 15 is phosphorus. So we already know that this is going to be P15. Now let's do the second part, right? So we know that the stuff on the top right here has to equal to the stuff on the top for this side. So you're going to say, let's say Y plus 1, right? Y plus this 1 on top equals to 4 plus 27, right? So you have to make sure the stuff on the bottom equals the same thing throughout, and the stuff on the top has to equal the same thing throughout. And solving this, you get Y equals 30. So this is your answer. Radioactive. So half-life is just how much time it takes for half of the nuclei in your sample to decay. So imagine if you have 100 nuclei, all right, in a sample. And what happens is, right, it's eventually going to decay into 50 nuclei over some period of time. And that period of time, when you're going from your original amount to half the amount you originally had, that's called half-life, okay? Half-life. So in this case, our half-life is 2.5 years, meaning that if we started out with 100 nuclei, if we wait 2.5 years, it's eventually going to decay into 50 nuclei. All right, so there's going to be 50 nuclei left. That's, that, let's say if this was, carbon, for example, after 2.5 years, there's going to be 50 nuclei that's carbon left, okay? And then over another 2.5 years, there's going to be 25 carbons left. And after that, 12.5 carbons left, okay? So that's kind of the thing. So if we go 10 years, right? If we go 10 years, 10 divided by 2.5, right? You're going to get 4, which means that this thing is going to decay. This thing is going to have 4 half-lives, okay? It's going to go through 4 cycles of decaying. So imagine if we have 100% of our nuclei. Then it's going to decay to half the amount. All right, so this is one cycle. Then it's going to decay to 1/4 the amount. This is the second cycle. Then it's going to decay to 1/8. That's the third cycle. And then 1/16. That's the fourth cycle. Right? And every one of these cycles, 2.5 years passed, right? This is 2.5 years, 5 years. Oh, sorry. 2.5 years, 5 years, 7.5 years, and then 10 years. So you can see how it matches up with what we have right here. This is going to decay to 1/16 of our original amount. Now we are moving on to the non-multiple choice questions. So based on table H, state the vapor pressure of ethanol at 75 degrees Celsius. Okay. So let's go to that. What was it? It was table what? Okay. So at 75 degrees Celsius, so right here, and ethanol is approximately, so if we look in this direction, 60, 70, 80 is about 85. Let's say 86 just to be safe. So 86, and then their units is kPa. So let's do it. kPa. So numerical setup for calculating the percent composition of mass of silicon and CiO2. So what is percent composition by mass exactly? So actually they have this formula in the reference guide. And yeah, percent composition by mass is mass of part divided by mass of whole. For example, if I have H2O and I was required to calculate the percent composition by mass, I would take of oxygen, let's just say for example, I would take the mass of oxygen, right? Oxygen's molar mass is 16 grams. And hydrogen's molar mass, right? So H2O's molar mass, that's going to be hydrogen's molar mass plus oxygen's molar mass, and it's going to be approximately 18 grams. And you multiply it by 100, and when you do so, put this into your calculator, you're going to get 88.9. 88.9. And all this tells you is that all this tells you is that water is 88.9% oxygen by mass, okay? So that's the percent composition. Now, we're only asked to do the numerical setup. So, let's do it. So the mass of part we're trying to find out is the SI. And how much does SI weigh? Well, SI is about 28.09. All right. So about 28.09. So 28.09 divided by the mass of the whole thing, that's 28.09, plus the mass of the oxygen, right? The mass of the oxygen, if you look in your periodic table, it's about 16. But because there's 2 oxygens right here, let's multiply that by 2. All right. So yeah, it's important to make sure that you multiply, let's say if we have, for example, 2 SI, then you would multiply this value by 2 and this value by 2. All right. If there was 3 oxygens, for example, you would multiply this 16 oxygens mass by 3. Okay. If there was, let's say, 4 oxygens, you would multiply the oxygen's mass by 4. So that's important to know. And you multiply this by 100, and that's your numerical setup. That looks good. Explain in terms of element classification why K2O is an ionic compound. Well, you have K, which is a metal, and you have O, which is a non-metal. So you can say that when a metal bonds to a non-metal, this creates an ionic compound. All right, and this is because K wants to give away an electron. Well, oxygen, it likes the electron, so it kind of takes in the electron, and the resulting cation and anion, right, are attracted to each other. State evidence from bright light spectra that indicates element A is not present in the mixture. So you have a mixture right here, and you have three elements, and you want to find out which elements are, in this case, why element A is not present in the mixture. All you got to do is make sure that, all right, for example, if we wanted to find out two elements that were present in this mixture right here, well, all you have to do is just match up the lines. And if the lines match up with the stuff in the mixture, that element is present in the mixture. And in this case, element D and element Z are present in the mixture because their lines, they match up, right? Their spectra lines up with the spectra of the mixture. But if you look at element A's lines does not match up with the spectra. So therefore, stating evidence from the chart right here, just say that element A's spectra doesn't match up with the mixture's spectra. That's why it doesn't work, right? These lines for A do not match up. Therefore, it's not present in the mixture. Explain why the spectrum produced by 1 gram. Okay. Now, imagine if element D, I don't know, I'm making this up. Let's say if element D was oxygen. All right. Let's say if element D was carbon. No matter how much oxygen you have, let's say 100 grams of oxygen or 200 grams of oxygen, the spectra is still going to be the same. So, explain why this spectrum produced by a 1 gram sample would have been the same spectral lines as wavelengths produced by 2 gram sample. Well, that's because it's the same element, right? Therefore, it has the same spectra lines. All right, that's the reason why. Doesn't matter how much of the element you have. If it's the same element, it's going to produce the same spectral lines. Okay. In terms of both electron energy states, how light from the spectral light is produced, and what happens is, all right. Imagine if you have an electron moving up an energy level. All right, so it moves further away from the nucleus of the atom. If it ever goes back down, it releases that energy, right, it gained as light, right? Because when an electron gains energy, it moves up to a higher energy level, and then when it goes back down in energy, when it goes back down to a lower energy level, it releases that energy as light. So how is the spectral lines produced? When electrons go to a higher energy level, right? Going back down to a lower energy level, it emits energy as light. All right, so that's how the light is produced. All right, in terms of valence electron, how do chemical bonds form in the substance of one? So we have a metal and we have a non-metal. So we know this is an ionic compound. And K is giving away one of its electrons to Br, which gladly accepts it. So we would say that K gives away one of its valence electrons, and Br accepts the valence electron, creating an ionic bond. Determine the total number of electrons in the bond between nitrogen atom and hydrogen atoms in diagram 2. Well, nitrogen has 3 bonds right here. You can see it has 1 bond, 2 bond, 3 bond. How many electrons are shared? Well, we'll just count the number of dots. 1, 2, 3, 4, 5, 6. terms of distribution of charge, why a molecule of a substance is nonpolar. Now, it turns out that some elements like electrons more than others and wants to snatch those electrons, right? It's like an adult taking candy from a toddler. If we were to look at diagram 2, nitrogen loves these electrons. So it kind of hogs these electrons, kind of like pulls them towards nitrogen, and it kind of grabs them from hydrogen a little bit. They're still sharing electrons, but the sharing of electrons is unequal. So hydrogen, because it kind of had its electrons stolen, it would have a partial positive charge. While nitrogen, because it's kind of like gaining all these electrons, as a partial negative charge. And this is a polar molecule. Now, this is a nonpolar molecule because the charge distribution is equal. Everybody's sharing the electrons equally. Therefore, the charge distribution is equal. So just say that the charge distribution is equal. All right. Draw a Lewis dot diagram for a molecule of Br. So Br, all right, has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Not 8. As said, 1, 2, 3, 4, 5, 6, 7, not 8. 1, 2, 3, 4, 5, 6, 7. And we have another one. 1, 2, 3, 4, 5, 6, 7. And these two bromine atoms, they can create a bond, right? They can share these two electrons. Because all atoms, they want a full valence shell. They want 8 electrons in its outermost shell. And when you're sharing an electron, it's kind of like you gained 2 electrons. So this bromine atom has 8 electrons from this bond right here. And this bromine atom also has 8 electrons if you do this bond, right? It can feel like it has a full valence shell. And then find a noble gas with the same positive ion. So in diagram 1, the positive ion is K+. Now in your periodic table, right, a K atom, a potassium atom, so let me just erase this real quick. A K atom has 19 electrons. And imagine if it forms a +1 charge. So it gives away one of its electrons, so it has 18 electrons left. But which atom has 18 electrons? Oh, argon. Alright, milliliters neutralized one. Alright, so when you're neutralizing an acid with a base, or if you're neutralizing a base with an acid, this is something called titration. This is something called a titration. And this is in our answer booklet, a neutralization reaction that occurred. Alright, so I don't got the answer booklet, but let's just say I give you this reaction. Write out the products of this reaction. This is also a neutralization reaction, by the way. Now, if you have a strong acid and a strong base, they're always going to form water, okay? They're always going to form water. So in any neutralization reaction, you're going to form water, and, right, it's like this is a double replacement reaction. They kind of swap partners, right? This OH kind of matches to the H, and the Na matches to the Cl. So it's going to form NaCl. All right, so this goes to here, this H goes to here. Now, you don't have to balance this equation because it's already balanced, right? So you don't have to balance, it's already balanced. The calculated molarity of HCl solution. Well, the HCl solution, let's see, calculated molarity of H should be expressed to what number of sig figs? Well, if we were to find the molarity of the HCl solution, we're using calculations that involve 3 sig digs, 3 sig digs, and 2 sig digs. And you're going to have to do like multiplication. And when you're doing multiplication, you got to round to the thing with the least number of sig digs. In this case, the thing with the least number of sig digs is 0.20. So you're going to round to 2 sig digs. So because 0.20 has 2 digits, 2 sig-digs, you're going to round to 2 sig-digs. Using this data to determine the concentration of HCl, we can see how the ratio between the acid and the base in this reaction, right, in this reaction we've written now, is 1:1. And when the mole ratio is 1:1, right, when the ratio of acid to the ratio of base is 1:1, you can actually use a formula. And this formula is also in your reference guide, thankfully. And this is, all right, and this is titration, MAVA-MBVB. All right, so our MA, all right, that's the molarity of acid. Well, we're trying to find that. Let's call this X. Times the volume of acid, well, 25 milliliters, so let's just say 25 divided by 1,000 liters, right? Let's convert it to liters, equals to the volume of the base times the molarity of the base, 0.20 molar. And we're going to round to 2 digits. So if you put this into your calculator, divided by 1,000 times 0.2 divided by 25 divided by 1,000, you're going to get 0.12 as your answer, to 0.12 molar. All right. And that's the concentration of the HCl solution. All right, state the location total charge of. So nickel has 28 protons. And so we can say that nickel, right? Well, where's the protons located? We have to state the location and the total charge of the protons in a nickel 64 atom. So nickel's protons, right? Any atom's protons. Let me just extend this. Nickel's protons are in the nucleus. Total charge is, well, protons are positively charged. So 28, right? You have 28 positive charges. So total charge is 28 plus, or plus 28, right? Positive 28 charge. Determine the number of neutrons and so the number of neutrons in an atom is, all right, so you have atomic mass minus your atomic number, and this gives you the number of neutrons, okay? So, all right, so in this case, our atomic mass, that's going to be 272, minus the atomic number, right, 111, that's going to give us the number of neutrons, which is 161. Based on the element produced by as a metalloid, or so we have to identify if the element produced by this nuclear reaction, so this element right here, we have to identify if Rg is a metalloid, or a noble gas. So let's go. Okay, I found Rg. This seems to be a metal, right? It's in the transition metals. All right, this is the transition metals. It's group 3 to 12. And anything in here is metal. So metal. All right, compare the entropy. Okay, so compare the entropy of the products to the entropy of reactants for this reaction. So entropy is the level of disorder in your system. And how I kind of think about it is, right, if we're talking about disorder, imagine if you have just a piece of solid. All right, solid ice cube. A solid ice cube will always look something like this, right? Solid ice cube will always look something like this. However, if you have gas particles, right, gas particles can move. They take the shape of the container, and they are pretty wild, and it can get pretty disordered. Like if you were to put gas particles in a room, it's going to spread out anywhere. It's going to get really disordered. It's going to get really messy, right? So the entropy, you would say that the entropy of, in this case, solid ice is going to be less than the entropy of this water vapor. And it turns out that gases have the highest entropy. All right, gases have the highest entropy, then liquids, and then finally the thing with the least amount of entropy is a solid. Okay, so least amount of entropy, it's in the middle, and gases have the highest entropy. So in this case, we're going from a liquid and we're going to a gas, and we know that a gas has a higher entropy than a liquid. So you would say that the entropy of products is greater than entropy of reactants. Determine the electronegativity difference. Oh, this is easy. NH. So if you go to your periodic table, we're looking for the electronegativity difference, and they give this to you in table S. Electronegativity of hydrogen is 2.2, and the electronegativity of nitrogen is 3.0. So the electronegativity difference is 3.0 minus 2.2, that's 0.8. And why is this very soluble in water? All you gotta know is that like dissolves like, okay? So if we have water is polar. Water is polar. And if you, let's say, put oil in water, oil is nonpolar. Therefore, this is the reason why oil and water don't mix, okay? This is why oil does not dissolve in water. Oil is nonpolar, water is polar. And because they have different polarities, they're not going to dissolve in each other. And the thing I want you to remember is like dissolves like. So polar things dissolve into polar things, and nonpolar things dissolve into nonpolar things. The reason why this is very soluble in water is because N2H4 is polar and water is polar as well. Like dissolves like. That's all you gotta put. Okay. In terms of IMF, so at a boiling point of this. Okay, all you have to say is that, alright, so think about it. If you're trying to go from a liquid to a gas, okay, what you're essentially doing, right, is you're breaking intermolecular forces. So why am I drawing there? My bad. Let's get this eraser. Alright, get this out. Alright, so let's say we have another water molecule. I think I explained this in my heating curve thing. But basically, when you're going from a liquid to a gas, you're breaking intermolecular forces between the molecules, right? You're completely breaking them. However, N2, right, hydrazine, N2H4 has stronger intermolecular forces, right? Stronger intermolecular forces than water. Therefore, right, if you have a molecule of N2H4, so it looks something like this. I'm not going to draw the lone pairs because I'm lazy. Right. So N2H4 has stronger intermolecular forces because, well, it has two hydrogen bondings. Okay, it has two locations of hydrogen bonding. You see, actually no, water also has two locations of hydrogen bonding. My bad. What I mean is that N2H4. All right, what I mean by this is N2H4 is overall bigger than H2O. You see, H2O, right? It has a molar mass of 18 grams. My bad. However, this thing, N2H4, weighs much more than this. So therefore, it's going to have stronger London dispersion forces, okay? They all have hydrogen bonding, but this thing is just simply bigger, and therefore its London dispersion force is going to kind of overpower the London dispersion forces of H2O. So I'm overcomplicating this a lot. Just say that the intermolecular forces for hydrazine is stronger than the intermolecular forces for water, making its boiling point higher. Okay? So the stronger the intermolecular forces, the higher the boiling point. Um, Laboratory technicians. Okay, so when you're saying that when you lower your thing into the solution, the light bulb glows brightly, and this means that this thing conducts electricity. Okay, so we're looking for something that conducts electricity. Oh, it can't be sulfur. It does not conduct electricity. Another portion. So if something melts at this temperature, that means its melting point has to be it has to be lower than 450 degrees Celsius, right? So the melting point of sodium nitrate is below 450 degrees Celsius. So therefore, the substance is sodium nitrate, right? If we used potassium chromate, right, its melting point is 974. And at that point, this thing wouldn't even have melted yet, right? We place this in an oven of 450 degrees Celsius, but this thing's melting point is 900. It's way above. This thing isn't even close to getting melted. So, yeah. Some one property. Well, the reason why it's necessary to use more than one property to identify the substance is because, right? Imagine if we didn't have, okay, so imagine if we didn't have melting point, right? Imagine if this column didn't exist. Well, we would think that we could use sodium nitrate and potassium chromate, right? We would identify the substance as either this or this, right? We don't have enough information if we only used two columns. So you would say that state evidence that makes it necessary to use more than one property. Oh, you would say that, I think you can just say that there wouldn't be enough information about the substances itself. Make All right. So you just say that there wouldn't be enough information. All right, that's why you need more than one property. And you can also state evidence from this thing right here. I'm not going to write a whole essay, but like just say, to kind of guarantee that you get the answer correct, just say that, the question talks about the conductivity tester and it talks about the melting point, so therefore you need more than one property. In terms of why, well, if you want something, imagine if we have this container filled with water. If we want something to conduct electricity, we need something that has a charge and it's moving. All right, we need something that has a charge and it's moving. In this case, in terms of ions, right? Ions have a charge and they move freely in water. All right, when you have a charge and when you have something that moves freely, right? The charge moves freely, it conducts electricity. All right. So potassium chromate conducts electric current, and I have to mention this, but potassium chromate dissociates so associates into ions. So basically, potassium chromate dissolves in water and it dissociates into ions. Okay, so it breaks up into a cation and an anion. And the ions, they have the charge and they move freely in water, so it conducts electricity. Now, how do I know potassium chromate dissolves in water? Well, you're going to have to go to table F now. And, all right, so we're looking at potassium chromate. Chromates, usually, they form solids, but they're combined with potassium, which is a group 1 element, and that's an exception, which means that these ions, right, K2CrO4, potassium chromate, when you dissolve in water, it actually does dissolve into ions, right? Normally, it wouldn't be an ion. It wouldn't dissolve into ions. Normally, if you have something bonded to a chromate, it's usually going to be insoluble or it's going to be a solid. But this is our exception. series. Natural gas. All right. So methane, ethane, propane, butane. They all have ane in its name. That kind of rhymed. And if we go down here, right? Anything ending with ane is an alkane, and alkanes have this formula. So yeah, just copy and paste this formula. All right. Right, it's an alkane, so it has to match this formula. That's the homologous series. An alkane. Structural carbon. So we're gonna draw butane, right? Because it's 2% natural gas. So butane, but, if you go in your reference guide, but means that your hydrocarbon, in this case, your hydrocarbon has 4 carbons in a row. And then because it's a alkane, right? Because it's an alkane, you can see from the example in table Q, all alkanes have just single bonds, and then the rest are going to be hydrogens, right? So this is an example of ethane, and butane, the rest would just be single bonds, and then you would have hydrogens on the end of it, on all of this. I'm not going to draw it all out, but you get the idea. Complete the reaction of sulfur trioxide of water. Okay, I don't have that question, so I'm just gonna write the formula of... Yeah, I don't have the answer booklet, so sadly we can't do that question. Final stretch. State evidence from the table. Components in a mixture. So imagine if you have a mixture of something. So a mixture is just 2 or more things physically combined, and for example, one example of a mixture would be lemonade. All right, and the proportions of a mixture can vary. So lemonade, it's not a compound because you can have 40% sugar, 60% water in lemonade, or you can have 50% sugar, 50% water in lemonade. Okay, so the proportions of a mixture don't have to be the same, right? It can vary. And from this chart right here, you can see how you can have different amounts of stuff in your mixture, which is why the proportions can vary. So you would just say evidence from the table, NH, you would just say that NH4Cl, right? You would say that there is a different amount of NH4Cl in both mixtures, meaning that the mixture, meaning that the component is varied, okay? The components are varied, okay? So you can have different amounts of stuff in your mixture. It doesn't have to be always like in proportion. What type of mixture is mixture B? Imagine if you have sand and you have water. You're going to see 2 distinct layers. All right? You're going to see 2 layers. You're going to see a water layer, you're going to see a sand layer. All right? And this, when you see 2 different layers in a solution, this is called a heterogeneous mixture. The other type of mixture is called a homogeneous mixture. And it's when you only see 1 layer in your mixture. All right, so if you only have 1 layer in your mixture, it's a why is my pronunciation so bad? That's homogeneous mixture. Homogeneous mixture. Okay. Homogeneous. So let me just write out the other mixture's name. Homogeneous. Alright, so you have heterogeneous, and you have homogeneous. Determine the temperature saturated solution. So for this problem, right, if it's talking about saturation, unsaturated, stuff like this, you should be thinking table G. Table G shows you how much of whatever thing, let's say in this case we're talking about NH4Cl, how much do you have to dissolve for it to create a saturated solution, right? Anything on these lines, all right, in this case, anything on this line means that your solution, if you add this much amount of it, it's going to start being saturated. A solution that's saturated just means that imagine if you dissolve salt in water. All right. Imagine if you dissolve salt in water. If you add too little salt, right, all the salt's going to dissolve and it just looks like pure water. You're not going to see anything. And this solution is called unsaturated. You haven't added enough of salt in this case. You haven't added enough solute, right? When you add just the perfect amount of salt so that there's a little bit of a salt clump, right? A salt precipitate, but you still have salt dissolving. This is something called saturated. This is when the solution is saturated. When the rate which the solid salt, when the rate of solid salt dissolving into the water is equal to the rate of the dissolved salt reforming back into a solid, okay? Just to repeat that, a saturated solution is just when the rate of which the solid precipitate breaks up and this dissolves in the water is equal to the rate at which the dissolved thing reforms back into a solid. And finally, you have supersaturated. This is when you add, imagine if you add too much water. Imagine if you add too much salt to the water, okay? Well, it's actually going to start forming crystals, all right? This is when you're supersaturated. Now, any point on the line means that you're saturated. In this case, we have to find out from a saturated solution in mixture A. Okay, so determine the temperature when mixture A dissolves to form a saturated solution, and you have 40 grams of it. So let's say we have 40 grams of it, and we're going to see when our point reaches the line. Ooh, it reached the line for NH4Cl, right? It reached this line right here. So what temperature does this become saturated at? Let's see, like 24, 25. Yeah, 24. All right, so 24 degrees Celsius is when this thing becomes saturated. One property of sand that would allow the students separate from other components. Imagine if you have sand and water, what can you do to separate it? You can filter it. Why can you filter it? Because sand is bigger than water. So you just say that the particles of sand are bigger than the particles of water, the molecules of water. All right, sand is bigger than water, and this difference in the particle size allows you to filter the sand from the water. State one benefit of using artificial leaf to produce hydrogen. It's an alternative energy source which replaces fossil fuels. This question is literally a reading comprehension question. All right. Right? Fossil fuels produce air pollution, right? Really bad. So scientists are using hydrogen as alternative fuel, right? It's an alternative energy source which replaces fossil fuels. That's the benefit. So in an electrolytic cell, what happens is, right, you usually have energy from a battery. And what happens is you're using the energy from the battery, that electrical energy, and you're fueling it for a reaction, all right? So you're taking the energy from the battery, the electrical energy. Let me write this down. So in an electrolytic cell, you're taking the electrical energy and you're converting that energy to power up a chemical reaction. So a chemical energy converts electrical energy into chemical energy. All right. Now, in this case, we're not using electrical energy. We're using energy from the sun. But explain in terms of energy why this is still an electrolytic cell. Well, you're taking energy and you're fueling it for a chemical reaction, right? Even though it might not be electrical energy, it's still energy. And you're taking energy and you're fueling it for a chemical reaction, right? Using it to fuel a chemical reaction. So you would say that you're using energy to fuel a reaction that doesn't happen on its own, or a non-spontaneous reaction. Are you using a reaction that does not happen on its own? Water doesn't just naturally break up into oxygen gas for protons and for electrons, right? You don't see water on the table doing that. You need this energy to fuel this reaction. Determine the oxidation number of oxygen during the reaction represented in equation 3. Well, oxygen, right? Oxygen is by itself, and it's in its natural state, so has an oxidation number of 0. And hydrogen has a charge of +1. And there's 2 hydrogens, right? 2 times 1 is 2. And we don't know the oxidation state of oxygen. So when you solve for x equals -2. Because you set this equation to 0 as this whole compound is neutral, right? The oxidation number of hydrogen has to add up with the oxidation number of oxygen so that this whole molecule of water is neutral. In this case, right, if we have a -2 here, -2 plus 2, that gives us 0. So this whole molecule is 0. So you would say that this went from oxidation number of 0 to -2, which is our oxygen. Oxygen's oxidation number, 99% of the time, is going to be -2 when it's bonded to something else. So that's also something you could have done. Oxygen starts out with 0, and it's almost always going to be -2 if it's bonded to another thing. And yeah, we finished it.